right. I'll go ahead and take this off. All right. Hello, everybody. Welcome to our next lecture for Robotics 102, Introduction to AI and Programming. So I just want to say it was fabulous seeing all of the people that got their robots working on Tuesday to do bug algorithm. It was great to see you do that navigation. For those of you who are still working on it, cool stuff. We'll get it working. We are the mode for the class is always about getting things working so that you understand what's going on, and we'll sort everything else out because I really care about your continued development and growth as a roboticist and AI practitioner, I guess we'll say. And so once we get your bug algorithm working on the robot, your bug navigation working, we're going to move on to breadth first search, to pathfinding for the robot. So what you notice with your bug algorithm, it does a reasonable job of doing navigation, but it's not perfect and it's definitely not optimal. We can do better, but in order to do better, we've got to build up some maps and we've got to be able to think about, have our robot reason through all the possibilities for getting to the goal and finding the route that will be the best. All right. Any questions before we get started? All right. Come on, man. All right. So for today, what we're going to do is we're going to have a we're going to go over the breadth first search algorithm. You should have watched the lecture that is now posted on the Slack channel. So this is a lecture on graph search. And so that lecture goes into more detail about the overalls for pathfinding and how we think about that in context, provides conceptual grounding. But what we want to do today is go through a more structured review of the breadth first search algorithm so you can get a good way of reviewing it. And then we're going to have a group activity. So I have these sheets right here that's going to be sort of a group activity that we go through to just get breadth first search working in our minds. And then what's going to become available to you is a repl.it with a C++ asynchronous activity for doing breadth first search that's sort of based on the example that we have here. And so just before we get into it, just a recap of like one of the main things from the lecture that's online and available for you is that we should note that our map is a robot map is stored as an image and represented as a graph. So if you see over here on the left-hand side is sort of like a real-world environment that we've set up with our real-world environment that we set up as an enclosure. And then if we run the robot through it, we can get a map that looks like this from the simultaneous localization and mapping system that will tell us what areas of space are occupied, which are cells listed in black, which areas are unoccupied in physical space, which are listed in white, and cells that we don't know if there's something there or not, which are shown in gray. One of the takeaways from the lecture is that we can then, if we want to start to do pathfinding, we can represent this map that we currently have as a graph. So every cell of space, we're gonna put a node inside of that, and that node is gonna represent any information that we have at that cell. Potentially, its XY location in the world. Whether that location is occupied. There's more information we have to put in there. We will represent that as a struct, and during lab we'll do a refresher on C++ struct so you can know how it's represented in this way. But we're going to have this graph, and then each adjacent cell, the node of each adjacent cell is going to have a link between them that's going to be connected by an edge. And so basically we're building up this grid structure of nodes at cells and edges that connect adjacent cells. And so that's what this looks like. And then once we have this structure, what we're going to do is a graph search we're going to do a search through the graph that's going to help us find a path to get from an arbitrary start location to an arbitrary goal location. So if we go to that node over there in the upper left-hand side, that could be a start location that we picked or where our robot currently is. And then we have a goal over here on the upper right-hand side. We want to be able to find a route from that start location to the goal, and that will not have our robot collide with anything. And so this is really what we do. I just snapshotted these from the lecture so you can see those. But so if you go in the lecture, I go through conceptually what this looks like for a number of different for this case, and I sort of walk through the algorithm on the whole. But I think one thing that might be good is just to go through a simple example on a simplified graph, so we can see what breadth first search looks like, and we can have sort of a grounded example of what this could be. So let's assume that we have a graph of this form right here. We've got I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes right here, listed A through I. And so you can even, if you can even count, you can count the number by singing the alphabet song, like A, B, C, D, E, F, G, H, I. That's number 9. So we've got nine nodes right there. Jana thought that was funny, so I thought that was good. And so we have nine nodes right there. And this is basically, this is represented as a tree. So a tree means we have no cycles, no loops in this. There's only connections that won't induce a cycle or a loop. And this is always, and we always in this case, we can always think of the top node, the A node, as the root of this tree. I'm going in a little bit more detail than I was expecting, but this is sort of this tree structure for our graph. And so we should note that we have the nodes. So we're just pointing out 3 of those nodes there. So A, B, and D right there. And then we also have edges that connect these nodes together. So that means that they have some form of adjacency or some form of direct connection. And with that, we're going to consider neighbors of a node to have shared an edge. So all the neighbors of a particular node are ones that share an edge. Okay. And so this is our graph structure for our simplified problem right now. And so if we want to find a path given this graph structure from node A to node H at the bottom here, we're going to walk through a breadth first search example to show you how to do that. To sort of show what this should look like. Did I hide that recite? No. So what we're going to do is we're going to have a number of structures that we need in order to make this happen. We're going to have a visit list, which is going to be represented as a vector, in particular a queue structure. We're going to have the current node that we're processing, and then we're going to have a collection of nodes that we've already processed, and we don't have to consider them anymore. Wait, did I miss something? Wait, I went too far. Right, and I think I talked without doing the transitions, but those are the nodes. The visit list has the nodes to visit. The current node is the current node we're processing, and then the visited nodes are the fully explored nodes. So to walk through what our breadth first search algorithm is going to do is we're going to first take our start node, which is going to be A in this case, the node we're going from, and we're going to add that to our visit list and set the distance to 0, because the start is 0 distance from itself. Once we do that, then we're going to pop off of the visit list the first node, which will be the start in this case, and then we're going to set that as the current node. Once we do that, we see if our current node is the goal. If it's the goal, that we found a path, great. Let's go ahead and return that path. So we're going to trace back from the goal node that we found as the current, and we're going to trace back to the start. If our current node is not the goal node, then what we're going to do is we're going to add each unvisited neighbor, each node that shares an edge with our current node but has not been visited before, and we're going to add that to the back of our visit list. Once we do that, we can then update we can set the routing for each neighbor as the parent. So we can say the current node is now going to link back to our route, and then we're going to add 1 to that neighbor's distance, and that's going to give us a routing table, right? And so this is roughly what we're going to do. We're going to start from our current location, from our start location. We're going to put that on our visit list, see if that's the goal. If it is the goal, great, we found a route. Let's return that to the robot. If we haven't found it, then we're going to process all the neighbors, and then we're going to update the routing information for those neighbors. And this is how our search algorithm is going to work. Everybody got it? All right, class is over. Thank you. No. No, let's actually go through an example so that we can make this a little bit more clear. So what we're going to do is we're going to start off, and I should say you'll learn the real breadth first search when you get to some of the upper level classes. This is just sort of the 102 version, just to be honest about it. But this is how it's going to work. So the first thing we do is we take our start location, start node, which is A, and we're going to add that to the visit list. We're going to set the distance from the distance at that node to be 0, because what the distance is going to represent is the distance along our route back to the start. And so if we're at the start, our distance is 0. All right. The next thing we're going to do is we're going to pop the last element off of our visit list, and we're going to set that as the current node. So A gets popped off our visit list, it becomes the current node. We then check to see whether that current node is the goal. So if our current node, which is A, was actually the node that we want to reach, which is H, then we can terminate the search and go on. But it's not, so we have to continue. So in that case, what we're going to do is we're going to take for the current node, what we're going to do is take each of its unvisited neighbors and add them to the back of the visit list. So what's going to happen in this case is we're going to take the neighbors, which are going to be B and C, and we're going to move them onto the visit list in an order that, I don't think you have to choose a particular order in this case, but we'll just put them on B and C. It could be C and B if we wanted to, but that's up to you. And so we add those onto the visit list, and then we're going to update them with the proper routing information. So because they were added on with A as the current node, we're going to say for B and C, their parent in the route is going to be element A, right? So they route back to element A, sort of like leaving a breadcrumb, right? And they are one step away from the start, so we're going to make their distance be 1. All right? Does that make sense? People got it? We've done breadth first search for 1 step at this point. That's amazing, isn't it? All right. I think it's amazing. All right. And so once we've done that, now we've fully processed element A, and we've processed node A, and so we can consider that off to the side. It's now in our set of visited nodes. We don't have to consider it anymore, right? So what we're going to do is now we're going to go back to step 2, and what we're going to do is then take our next element off of the visit list. So that will be element B. So we take element B off, and then C moves up in the visit list. We can then check to see whether our current node B is the same as our goal node H. It's not, so we then can continue along with our iteration for the algorithm. So what we're going to do is then for element B, we're going to add its unvisited neighbors to the back of the visit list. So in this case, if we look at B, there's D and E, which are the unvisited neighbors. We can then add those onto the visit list, right? And so those are now on the visit list. And then we can update their routing information. So now we can update their routing information. So because node B is 1 element, we can set the parent of each of those nodes, C and D and E, to route through element B. That's going to be the parent, right? And then we're going to update the distance. So B, we know that B, which is the parent, has distance 1 from the start. Now its elements are going to be 1 more away from the start if we route through B. So now they're going to take on distance 2. All right. And so this is now once we've done that, we've fully processed B, and we've done our search all the way through that node. And so we can consider B to now be visited, and now we can pull the next element, the next node, off of the visit list. And so if we do that, our next element that we pull off the visit list will be C. So we can take C off the visit list, and then move all the other elements up. And then if we take, and then for element C, if we can see if that's the goal node H, which it's not, so we can then continue. For element C, what we'll do is we'll add each of its unvisited neighbors to the back of the visit list. So that means element F, node F, will go to the back of the visit list, and then we'll update that information for that node F to now be, all right, did that not update? We'll update that element to now have node C as its parent, as its routing parent, its routing via point, and then it'll have distance 2 because there's now 2 hops away from the start. Okay. Any questions at this point? Great. So now once we do that, we can consider node C to then be processed, and then we can then take our next element off the visit list. So if we take our next element off the visit list, that's element D, move everything else up on the visit list. Now we can add each unvisited neighbor. What are the unvisited neighbors of D? What's that? There's none. Thank you. And so then so if we don't have, so if there's no neighbors, we don't have to do any updating in the route. And so we can then move on to our next element. So once we do that, then we have our next element on the list, which is going to be E. We pop that off. And then we move F up. So then then for E, we can then process that. If we look and we say, well, what are the elements of E that are neighbors? Anybody want to tell me the elements of E that are unvisited neighbors? Adi again. What's that? G. So now we'll pull G onto the visit list, and then we'll update its routing information to go through E. Oh, there we go. And it's going to have distance 3 because now it is 3 hops away from the start. Three edges, edge transitions from the start. Right? So once we do that, we can now go to 2. You can't see the top there because the zoom is hiding it, but I've just expanded everything out. So steps 2 through 5. And so you can just see it right there. So what's going to happen at this point? What's going to be, what's our new current node? Anybody? Can you save these people? F, thank you. So F becomes our current node. And what's our routing information? So what new neighbor do we put on? What's that? H and I. Great. So H and I then come up, and they all have distance 3. Great. All right. What happens now? Somebody help me. I'm drowning. All right, upper level computer science student.
Well, would it break, or would it have to see at the current stage?
We'll get into that point, but what happens now that we've currently done all of this? What happens next? We've completely processed F. Right, so F goes away. We bring up G. What's going to happen when we process G? Wait, somebody say that a little bit louder. Go ahead. Right, so that's pretty much we don't have any nodes to process now because G doesn't have any unvisited neighbors. All right, what happens now when we get to this point? Now we've popped off H. What happens now? So we're at H. That is now the goal node. Great, right? And so now we find the path. How do we find that path? Right. So now that we've done this, we can now skip to step 6, and we're going to trace backward through the parents. So if we look at node H right here, right? What's the parent? I can't read that because I'm in my late 40s, but what's the parent of H? F. So we're gonna put F as our next element. What's the parent of F? C. So we can read that off. And then what's the parent of C? What's that? A. There we go. And if we did that, we found our path. I don't know why that animation played so fast. So there we've got our path. And now with that path, we found a route and we know the distance along the route. And so that is really what our breadth first search algorithm is doing. And that's what you're going to code up. And that's what we're going to code up for project 3. Right? Okay, but here's a question. What if our graph has loops? What if we've got a loopy graph? How's that going to impact our algorithm? My upper level computer science students can answer this one. Maybe. Yeah. That does mean that one element could potentially have multiple parents, but we're only going to choose one. We will choose the one that leads to the shortest path. So that is the parent that we want. So what we're going to do in order to make that happen is we're only going to update the neighbor's parent and distance if its distance is greater than if its distance is greater than 1, then the current node's distance plus 1. Is that right? Can you read that for me? That makes sense? So we're going to update the parent's distance only if its distance is greater than the current node plus 1. That's right. Right. So and you should note this is only the case. This only applies to the case where the edges have distance 1. If we start changing the distances, right, then that will if we have different edge distances, then this breaks down a little bit. But this is what we're going to do here. I always have to read this and reread this to make sure. I've been doing this for decades now, and I still don't. Still have to read it again. Yeah.
We have E or F, and then process H, the distance will be 4. That's a conflict. How we resolve that?
By doing this. So we only update when we have a better distance, right? When we have a better route. So we'll show an example of this, right? So we will update the parent routing if we get a better route, right? Let me go through the example and we'll see it. Okay. Other questions? All right. So what this is going to mean is that we're going to look at our neighbor's distance and make sure that it is greater than the current distance plus 1. And if it's not, then we don't then we can update. Otherwise, we don't. So let's walk through what this will look like. So what's the first thing that happens when we start off? Yeah, in the back. We're going to visit A. So that means we will put A onto our visit list. We will pop it off and it becomes the current node. And as we pop it off, we're going to update the routing. We're going to add B and C, our neighbors to the visit list, and we're going to update their routing to go through A with distance 1. All right. What happens next? You want to tell me what happens next? All right, and we go to B because B is the next item on our visit list. So once we do that, B comes down, and then we're going to process its elements. And so we have its neighbors, and so I can't read that, but I'm going to assume that's D and E. And so we update those, and we put them on the list. One thing I forgot to say that's really important is that what we're doing is maintaining a distance. We have to maintain the distance at every node, right? So we initialize every distance to start off with some really high value. I don't know how to represent infinity in C. I know there's some constant to do that. Usually I just set it to be some really high value, like, you know, like a million or something like that. I don't know, but or if you're an integer, it's, you know, some max end. But you know, but as we go along, as we find a better route for updating each element, we update those values, and it goes, and that initialization goes from taking the distance to be some extremely high value to the actual value along the route, and so that's why you see the infinities there. All right, so once we do that, we've processed B. We've updated the neighbors. We've enqueued them onto the visit list. Now we can take our next element off, which is going to be C, and we're going to update its elements that are going to be on here. So now with C, we're the neighbors of C that we're going to have to think about. Neighbors of C, H and F, right? Reading that. And so now we come to this case right now where we've got, right? Now when we update that, we update for H, we have a route that's going to be 3 in distance, that 3 or 2, 2 in distance, I'm sorry. And so now we have a pretty good route right there, right? But we're going to encounter other routes that are going to be higher in distance. So now as we go along, we have D, right? D has no elements for us to enqueue, so we move on. Then we go to E. E is going to then enqueue G and node G, and then from G we're going to update its distance. And note that we could have enqueued H, right? But it's already visited, and we don't really want to update its value, right? Because if we're going to do the routing, if we do a routing through E, now we're going to take on a distance of 3. Is that 3? Is that 3 or 4? No, 3. H to E to B to A. 3, thank you. Right, I have to do that every time. People think that, you know, that because you've done this for decades, that it just is natural and it's fluent. No, I have to constantly, the same way when I'm doing linear algebra, I still have to finger sweep matrices to multiply them. Anyway, that's a digression for my students in Rob 101. That's just for you. But we don't update because because our routing through C is going to be better, right? Just 2 hops instead of taking 3. One way to think about this, to just make it sort of more natural, is that if, you know, imagine this is, you know, that you're looking at flights, right? So I could get a flight if I'm trying to fly from, let's say, you know, I'm trying to fly from Lansing to Miami, right? I could get the routing that just takes me through Detroit, which would be C, you know, A to C, and that would be a great route. But, you know, I might get another route that says, you know, that I have to go Lansing to Chicago to Denver and then to Miami, right? Why would I do that? I would always stay with the route that's better, right? Yeah.
So basically, we're updating the distance we find the shorter.
Exactly. We're just to repeat, yeah, you're only updating the distance if you find a shorter distance, right? But because these are one unit distances, right? Just one element. Think of it more as like you know, like bus trips or flights, as opposed to actual distance. Okay. So as we move along, so we're going to keep our current parent in distance. We move along, and then so now we get to node F. So if we look at node F, we'll notice again that offers a route that will enqueue I into the visit list, but it will also present another route, another possible route through F that's not going to be better. So we're going to keep our current route and not update. And so then we move, and then we find our goal, node H. We found our route, and we can trace back and get our route back to A, which is going to be faster, right? So we can handle these loops with this little augmentation to breadth first search. So with that, I would like us to do to do a bit of a group activity here. So I've got sheets of paper right now that I'm going to pass out. Or you have a question before we do this? Yeah. Yeah.
Since all the edges are like distance one,
Right.
companies said like instead of keeping track of distance, like, when we reach node E, we can like recognize that H is in the visit list and just not like process it as opposed to like keeping track of a distance for every node.
Well, you might not get the best route. Because let's say that instead of in-queuing, you know, you said, well, I got to think about that. All right, I'm not going to answer that. I'm not going to answer that on during class. I'm going to answer offline because I just realized if I'm looking at this and from over here, I could just be making up stuff. I want to give you a good answer, so I'll answer that offline.
C would reach
Yeah.
H before, so then C would add H to like the visit list, and then so by the time you get to E, like he can see that H has been visited and not added again to the visit.
That's true. But part of the reason why we think about it this way is that we want to go through and process our nodes and make sure that because there could be a better route if we start changing these distances on the edges. So we'd like to keep a consistent formalization. But you're right, we could take some shortcuts. It's a tree data structure. This is a tree, but a tree is a particular type of graph, right? If you're asking me in terms of a data structure that you would represent in C++, there's different ways that you could represent the tree in code. And we're going to only talk about one way to do that. But I'd leave that for a 280 topic.
And the visit list is a stack.
Visit list is a queue. So a stack is first in, last out. A queue is first in, first out. Okay. All right. So let me go to our group activity. So now I'm gonna pass out this. We're gonna do this. We're gonna do our group activity here. And so we've got Michigan here, and what I want people to be able to do is we're gonna find some routes. And in particular, we're going to find a route. I think we're going to go from Ann Arbor to Marquette. And so we want you to go through the process manually. We're going to leave the algorithm up here. We want people to get together in groups and be able to work through this together, just pencil and paper. And then after that, we'll have an assignment, just an activity for you to do this in code. Note that we have edge distances here, right? But let's think about this first as bus trips, right? I'm going to take a bus trip. How many bus trips would it take for me to get from Ann Arbor to Marquette? And so with that, I'm going to pass these out, and I'm going to ask you to get in groups. We want groups of 2. Is that good? All right. So find a partner, but you have to find somebody on the other side of the room to partner with, and get a pen. And we're going to do this real quick. All right.